Welcome to this exploration of the paper that unlocked deep learning, focusing on the backpropagation algorithm. In 1986, David Rumelhart, Geoffrey Hinton, and Ronald Williams published Learning Representations by Backpropagating Errors in Nature. This paper popularized backpropagation, the algorithm that enables neural networks to learn from data. Every deep learning system today, from image recognition to language models, uses backpropagation. Since the 1950s, researchers dreamed of machines that could learn like brains. Frank Rosenblatt's perceptrons in 1958 showed single-layer neural networks could learn simple patterns. However, Minsky and Papert in 1969 proved perceptrons couldn't learn certain functions, like XOR, which stalled neural network research for over a decade. Multi-layer networks could learn complex functions, but the challenge was how to train them effectively. The core problem was the credit assignment problem. How do you determine which weights in a multi-layer network are responsible for errors and need adjustment? The output layer is easy to adjust, but hidden layers don't have direct targets, making it difficult to assign blame for errors. The key insight of backpropagation was to use the chain rule of calculus. This involves a forward pass to compute the network's output, followed by a backward pass to compute how much each weight contributed to the error, layer by layer. The error signal propagates backward through the network, hence the name backpropagation. The chain rule allows computing gradients for every weight, no matter how deep the network, by multiplying derivatives along the path to the output. The algorithm consists of three main steps: a forward pass, a backward pass, and updating the weights. First, the forward pass feeds input through the network, computing each layer's activations, output, and error. Next, the backward pass computes the gradient of error with respect to output layer weights, then propagates these gradients backward through hidden layers using the chain rule. Finally, weights are adjusted proportionally to their gradients. New weight equals old weight, minus learning rate times gradient. For backpropagation to work, activation functions must be differentiable. Before, perceptrons used non-differentiable step functions, but backpropagation requires smooth functions like sigmoid, tan, and later ReLU. The paper's title emphasizes learning representations, meaning hidden layers learn to represent inputs in ways useful for the task. For digit recognition, early layers might detect edges, middle layers curves, and late layers digit parts, all discovered through training. The paper demonstrated backpropagation on tasks like the XOR problem, binary encoding, and family tree relationships, showing networks could learn internal representations automatically. While backpropagation wasn't entirely new, the 1986 Nature paper by Rumelhart, Hinton, and Williams brought it widespread attention. It was part of the connectionist movement, emphasizing intelligence emerging from simple units and knowledge distributed across connections. Backpropagation succeeds due to gradient descent, compositionality, differentiability, weight sharing, and representation learning. However, the paper acknowledged limitations like local minima, vanishing gradients, biological implausibility, and slow training. Despite initial excitement, neural networks faced a winter in the 1990s and 2000s as other methods proved more practical. The revival came in the 2000s, 2010s with Hinton's deep belief networks, faster training with GPUs, and AlexNet's victory in 2012. Modern deep learning uses backpropagation with enhancements like better activations, optimizers, regularization, and architectures. Frameworks like PyTorch and TensorFlow compute gradients automatically through automatic differentiation, industrializing backpropagation. Geoffrey Hinton, a co-author of the 1986 paper, continued to push neural networks, earning the Turing Award in 2018 and the Nobel Prize in Physics in 2024. The 1986 paper's legacy includes efficient gradient computation, the concept of learning representations, and the framework for deep learning. Its key insights define modern deep learning. Multi-layer networks can learn complex functions. The chain rule enables efficient gradient computation. Representations emerge from training, and learning is optimization. From theoretical proof in 1986 to AlexNet's practical power in 2012, and today's GPT-4 and AlphaFold, backpropagation is everywhere. The 1986 paper by Rumelhart, Hinton, and Williams solved the credit assignment problem, making the dream of learning machines achievable. When AI writes text, drives cars, or recognizes faces, backpropagation is running, thanks to 3 researchers who gave us the algorithm that made machines learn.